Okay, so the last video in the series is going to be dealing with the Hammond Postulate. And in a nutshell, what the Hammond Postulate states is this, is that the transition state will resemble um, the species that it's closest in energy to. So basically, if it's closer in energy to the reactants, then it's going to resemble the reactants. If it's closer in energy to the product, then it's going to resemble the product. So let's take a look. So here's an exothermic reaction, right? And so you see here, you have your reactants, you have your products, you have your transition state. Now let's get this out of the way and look here, right? If you look here for exothermic reaction, right, the energy gap between the reactants and the transition state is very small when we compare it to the energy gap between the products and the transition state. And so for an exothermic reaction, the Hammond postulate simply states that there is minimal bond breaking and bond making. We can make that assumption because the transition state resembles the reactants, right? And then we call this type of transition state early. So an early transition state. So that means that the the transition state doesn't look much like the product. It looks a lot more like the reactants, right? And this is for an exothermic reaction, right? So let's look at the converse of this and talk about an endothermic reaction, right? So again, we're talking about the Hammond postulate, and what we're saying is that the transition state is going to resemble the species, be it reactants or products, that is closest to an energy, right? So let's look at the energy difference here. All right, notice between the products and the transition state, the energy gap is much smaller, right? Now let's compare that to the gap between the reactants and the transition state. Remember, for an endothermic reaction, the activation energy is a lot higher, right? So the difference in energy between the reactants and the transition state is going to be much greater, right? So the Hammond postulate says we can take away from that the Hammond postulate this, right? That for an endothermic reaction, there's extensive bond breaking and making in the transition state. And since the transition state is closer in energy to the product, it resembles the products. And we call this a late transition state, right? So for an endothermic reaction, there's a late transition state. All right, so let's make this realistic. All right, let's talk about the Hammond postulate in relation to the club, right? And I'll make an analogy here. So you're at the club, and not you personally, but you know this happens all the time. Someone may go to a nightclub, they're dancing, right? They're having a few drinks, and they meet this person, and all of a sudden they're at the motel, and the sun is coming up the next thing you know, right? And so I like to relate the Hammond postulate to a one-night stand, right? Let's watch it. Notice it's very fast. For exothermic reaction, the Hammond postulate says that there's not a whole lot of bond breaking and bond making in the transition state. It really looks like what you start with, the reactants. So because the transition state is closer in energy to the reactants, there's minimal energy to get to the transition state, not a lot of bond making. It's a much faster reaction, and so I liken it to a one-night stand, right? It doesn't take much energy to do this, all right? There's not much of a connection after that one-night stand is over. And so what I'm trying to say is that because the reactants resemble the transition state and there's not a lot of bond making and bond breaking, it's almost like a little rendezvous, you know. You meet, things happen, and then you never see that person again. So remember, for an exothermic reaction, it's a really fast reaction, and remember that the transition state resembles the reactants. All right, so let's make this clearer. So Hammond postulate as it relates to the relationship. So let's say that you meet someone, you all date, you hold hands, you get to know one another. Eventually, maybe you get married, and there's a much deeper connection there, right? That's what happens in an endothermic reaction, right? Remember, it's a much slower reaction, right? Takes a lot longer, a lot more activation energy to get to the transition state. And so we say that the transition state is late because there's extensive bond breaking and bond making in the transition state. So I liken that endothermic reaction to a relationship because it takes a lot more energy to have a relationship than it does to take than it takes to have a one night stand. All right. So hope that makes sense. So let's recap. All right. So let's talk about kinetics. We've talked about kinetics. We've talked about the rate and rate constant kinetics, dealing with the rate of change of R into P. We've talked about endothermic and exothermic reactions. We've also talked about how to interpret um, reaction energy diagrams, and then we wrapped up with the Hammond postulate, dealing with a late transition state versus an early transition state. Right? Remember, for the Hammond postulate, if the transition state is late, that means that the reaction is endothermic, and then if the transition state is early, that means the reaction is exothermic. All right. So I'm going to put a short quiz on Blackboard for tomorrow dealing with these three videos. It'll be about maybe 3 or 4 questions. And if you have any questions, you can always tweet me, you can email me, or you can come by the office. And hopefully this made some sense to you. So I'll see you in class. Peace.